Let's move on to chapter 5 now. Here we will deepen our understanding of ranks and inverses of matrices. But this is actually the second part of the algebraic picture of linear algebra, which means we will be actually solving equations. Before getting into the concept of the rank of a matrix, let's just recap what we did last week, which was Gaussian elimination, whereby we took a matrix, did a series of row operations, and ended up with an upper triangular matrix. To the extent that a matrix represents a system of linear equations, this helps you in determining whether the system can be solved and what kind of solutions you will have, and also in actually helping you solve the underlying equations. To do the underlying equations, the solutions of underlying equations, you had to back substitute. But it turns out that back substitution also is something like row operations. So that can also be codified as a part of an algorithm. That algorithm is called Gauss-Jordan elimination. So you go forward, starting from the top row, go downward to get an upper triangular matrix. And then you start from the bottom row and then go backward up, that is back substitution, and do a series of operations, row operations, so that you can actually get the final solution of the system of linear equations. And that's what we will learn here. But along the way, we will understand the concept of the rank of a matrix. So let's redefine it to begin with. We already saw last week that rank is just the number of pivots. We also saw that if a row is a linear combination of the other rows in the matrix, then it gets killed in a sense that it becomes a zero row by the algorithm, by the series of elementary row operations that we perform. And that is basically how Gaussian elimination works. And then the zero row will get pushed down to the bottom of the matrix. So the idea is that any row that is a linear combination, by following the steps in the algorithm, will become a zero row. So any row that doesn't become a zero row is not a linear combination. And as we know that the definition of the pivot is the first non-zero element in a row in the REF, in the row echelon form, that means any row that is not a linear combination of other rows will have a pivot because it's not zero. So there will be some first element somewhere in the row that is not zero. That will be the pivot. So the number of pivots is the same as the number of rows that are not linear combinations of other rows. What does that mean? If a row is a linear combination of other rows, then that means that row is linearly dependent on other rows. To put it differently, a row that is not a linear combination of other rows is linearly independent of the other rows. So the number of pivots is actually the same as the number of linearly independent rows of the matrix. So remember our elementary row operations, EROs, where the first one, swap any two rows, which we had to do if in the pivot position we had a zero, then we had to do this. Then the second operation, multiplying a row by a scalar, scaling a row, we tried not to do. Actually, we did not do. The first one we tried to avoid, but there were situations where we could not avoid, as you saw in our interactive visualization. The last one, adding a multiple of a row to another row, was the one that we used most, and that is the one that made linearly dependent rows zero rows. So as we kind of establish, all non-zero rows in REF after Gaussian elimination will have pivots because the definition of the pivot is the first non-zero element in a row in the REF, and this statement just follows by definition. So we can actually state that the rank of a matrix is the number of linearly independent rows of that matrix. That's where I wanted to get to in this slide. So we went through a convoluted path, but we reached there. So since we are talking about the number of linearly independent rows, we can call that the row rank. Then similarly, you can think of having a column rank, which would be number of linearly independent columns. Then there is a famous theorem in linear algebra that says the row rank is the same as the column rank, so we just have to talk about the rank. If you look at it from the perspective of the rank being the number of pivots, you can see that the row rank will be the number of rows with pivots. Column rank will be the number of columns with pivots. And whether you look at the pivots from the top, column-wise, or from the side, row-wise, it's the same pivot, so it's the same number. So the row rank is the same as column rank. So it's kind of obvious when you come at it from the angle of pivots, but it can be proven in other ways also. Something to keep in mind for our purposes is that most data matrices that we will come across are tall. Tall in a sense, you will have more rows than columns. This is kind of obvious because we are dealing with measurements along some features. That will be a set number of features, let's say 5 or 10 or 100 or something along those lines. And then you will have observations coming in. Observations can be thousands or millions. So typically our data matrices are tall. So the best we can hope to have is a full column rank matrix, or the rank will be the same as the number of columns. In fact, most data matrices will have that property because the data are actually just measurements, and measurements typically suffer from things like statistical fluctuations or measurement errors. So it's very hard to get two columns absolutely identical or even linear combinations of other columns. So it's unlikely that you will have less than full column rank in a data matrix. But nothing in life is black or white. There are shades of gray in between. What I mean is that it's possible that one feature by construction or by accident is dependent on other features. Let me give you an example. Suppose I make measurements of your weight, your height, your age, and the length of your hair. Now, what's going to happen is that girls in my class tend to be a bit smaller, a bit lighter, and a bit younger because this is Singapore and we have national service for boys. They also tend to have longer hair. So the length of the hair will have some dependence on the other three. And it's possible that there will be high correlation. It's not that the length of the hair, that column will be a linear combination, but it'll be something close to that. This is called multicollinearity in data science. And this has got some implications in linear regression, the stability of some numerical methods, etc. What I'm trying to say is that even in data matrices, you have something like linear combinations coming in for some columns being linear combinations of other columns, but not completely, not 100%, but it is a scale that runs from 0, in which case this is totally independent of other columns, or close to 1 when it suffers from some kind of multicollinearity there. But we also saw, coming back to our rank thingy, that the rank of a matrix cannot be greater than the number of rows or number of columns, because you cannot have more pivots than rows, because each row can have only one non-zero first element at best. It could be a 0 row, in which case it may not have any pivots, or one pivot. So the number of pivots that you can have cannot be more than the number of rows, or to put it even more simply, you cannot have more linearly independent rows than the total number of rows that you have. Similarly, you cannot have more linearly independent columns than the number of columns that you have. So the rank of a matrix is at most the minimum of the number of rows or the number of columns. Now let's look at some properties of ranks, some useful properties. One is that if you have two matrices of the same size, take the sum of the two matrices. You can add them only if they have same size. Then the rank of the sum is less than or equal to the rank of the first matrix plus the rank of the second matrix. This may not be completely obvious when I put it in this abstract matrix lingo. So let's take an example. Suppose I take the first matrix A as almost like the identity matrix in 3 by 3, except that the last column, last element, I zeroed it. So it's like two columns of the identity matrix and a 0 column. So the rank of that matrix, what's the rank of that matrix? Only two linearly dependent columns or rows. So the rank is 2 out of the possible 3. And let's take second matrix B, again as an identity matrix. This time I'm going to zero the first 2 rows and 2 columns, same thing. So there's only one last column that is the same as the identity matrix. So the rank is 1. So if we add these two matrices, of course you get the identity matrix, and the rank is 3. 3 of course is less than rank of A, namely 2, plus rank of B, namely 1. Let's expand on this theme a little bit more. Let's take the second matrix B, not just the last column. Let's take it as the identity matrix, the whole identity matrix. So its rank is 3. But what is A plus B now? A plus B is going to be a matrix that has got 2, 2, and 1 along the diagonal and zeros everywhere else. But what's the rank of this matrix? The 3 rows and 3 columns are linearly independent, so the rank is 3. So on the left-hand side, you have 3. On the right-hand side, you have 2 plus 3, 5. And 3 is, of course, less than or equal to 5. So that is the illustration. And I just wanted you to get this idea clear in your mind that it is actually true. But the application of that is much more interesting. If I have a matrix of rank R, it can be written as a sum of R rank 1 matrices. You can somehow decompose it into rank 1 matrices, and you will need R of them. You don't need more than that. You can have more than that if you want, but you don't need any more than that. Even now, the application may not be that obvious. Let's take another example here. Let's say we're talking about an image, a grayscale image, and a grayscale image. Let's say the sizes are modest, say 100 by 100. And since it's an image, it's likely that it will probably have a rank close to 100. So you can actually write it as a sum of 100 rank 1 matrices. But it's possible that some of those matrices have very little weightage in the actual quality of the image. If you actually sort it in terms of the importance of the rank 1 matrices in the final image, maybe you need only the first 5 of them or first 10 of them. How you would sort it, what criteria you will use in sorting those things will come much later in this course, but it can be done mathematically, not just computationally, but mathematically. What that means is that instead of taking a rank 100 matrix, you can actually take just 5 rank 1 matrices, which will have much smaller memory requirement, memory footprint, and that will be a data compression algorithm. It is actually used in that context in certain cases. The second one is very important. It's kind of mathematical or theoretical, but it is used all over the place in computer science as well. It's that the rank of A transpose A and A transpose and A transpose, they all have the same rank. So the last two, A and A transpose, that is kind of obvious because you have a certain number of pivots in A, you just transpose it, you have the same number of pivots, that's okay. But the fact that A transpose A and A transpose have the same rank can be used in certain situations. Again, for a data matrix, a tall matrix, what's the size of A transpose A? It'll be the number of columns, but a square matrix with a number of columns the same as the original matrix, number of rows also the same as the number of columns of the original matrix. And since we know that data matrices are likely to be full rank, A transpose A is going to be a full rank square matrix with the same rank as the original matrix. And this matrix is called gram matrix. It's got many applications in machine learning. I highlighted something about the gram matrix being proportional to the covariance matrix of the data, which makes sense because it's got n features. So n by n matrix, covariance matrix is supposed to be n by n. But of course, you have to do some pre-processing before you can actually get the covariance. Then it also has got some implications in neural networks, etc. But what about the matrix A transpose? What's its size? It's going to be the same as the number of rows as the number of rows of A transpose and the number of columns. So it's going to be size m by m. M is a bigger number, but the rank is only n, which is much smaller than m. So it's going to be a horribly rank deficient matrix, but still the rank is going to be n. Interesting. Now there's some other properties that I called academic. It's the fact that the only zero rank matrix that you can come up with is a zero matrix. That's the only matrix that will not have any pivots anywhere. The second thing is that if two matrices are conformant for multiplication, then I can make the statement that the rank of the product is less than the minimum of the rank of either one of the matrices. Well, this is true in general. In our case, let's take our favorite equation, Ax equal to B. A is a matrix, X is a vector, which is a column matrix. What's the rank of a column matrix? It has to be 1 because there's only one column, unless it's a zero matrix, zero vector, in which case the rank would be 0. So what's the rank of the product Ax? It has to be 1 because B in this case is actually X and that has rank 1. So this guy has got rank 1. So regardless of what rank A has, full rank or otherwise, anything other than 0, Ax will have a rank of 1, which is kind of obvious because we are writing Ax equal to B, B being a column vector, and that has a rank of 1. Now, if B is a full column rank matrix with enough columns to hold the rank of A, with more columns than the rank of A that is, then we can say that rank of AB is the rank of A. So that condition is important because, as we saw, if B is a column matrix, a vector, then the product has a rank of 1. But if B is not a vector but a series of vectors, enough vectors to hold the rank, if more than the rank of A, then AB will have the rank of A. Similarly, if B is a full row rank, the rank of BA will be the rank of A, always providing that B has enough rows or columns to hold the rank, to preserve the rank of A. It comes from our original statement here, and also from the column picture and the row picture, as the case may be. Now let's look at the shapes of matrices and what that says about the largest rank it can have. A tall matrix, our favorite shape. We have A in M by N. M is greater than N, more rows than columns. If the columns are linearly independent, we can call that a full column rank matrix, and we will actually call that a full rank matrix because column rank is the same as a row rank. And most data matrices will have full rank for reasons that we expanded on earlier. Typically, in this case, Ax equal to B cannot have solutions because there are too many equations, and all those equations are independent and therefore inconsistent. But you still have to use all the equations together and you come up with some best approximation to the solution, and that is the game we will play in linear regression. That exactly is what linear regression is. Now you take wide matrices. If all the rows are linearly independent, of course in wide matrices you have more columns than rows, and remember, rows are equations and columns are unknowns. If the rows are linearly independent, there will never be a zero row in the REF, so there is no chance of having 0 equal to non-zero in the augmented matrix, regardless of what B you take, what constants vector you take. So this is never going to be inconsistent. There will always be solutions. And what kind of solutions? Because you have more unknowns than equations, the system of linear equations is not constrained enough, so you will always have an infinity of solutions. So fewer equations than unknowns, underspecified, underconstrained. Now let's talk about rank deficiency. Suppose you have a square matrix n by n. The rank has to be less than or equal to n. If the rank is actually n, then it's a full rank matrix. It's full column rank, full row rank. If not, the rank deficiency is n, which is the maximum rank it could have, minus the actual rank that it does have. In the case of a tall matrix, the maximum rank it can have is the number of columns. But if the rank is actually less than the number of columns, then again, n minus r would be the rank deficiency. If it's a wide matrix, the maximum rank it can have would be the number of rows, not the number of columns. In that case, if it doesn't have rank equal to the number of rows, then the rank deficiency is the number of rows minus the actual rank, m minus r. If a matrix has full column rank or full row rank, we will call it a full rank matrix. So that completes the discussion on the rank of a matrix and its properties. Now, like I said, this chapter is actually on the extension of Gaussian elimination called Gauss-Jordan elimination. That's where we will go in the next video.